As Brent already said, I'm Paolo. The weird city where I come from is the little tiny dot from Italy. Funny jokes, the other 19 regions in Italy pretend we don't exist. Don't ask me why, but that's how it is. You can find me online on P_Insogna on Twitter and Shogun Panda on GitHub. Reach out to me anytime. I want to thank Nearform, which is my company, who sent me here in Utah. We are a globally delivery and consultancy company focused on high quality, open source based consultancy. We are 300 and counting people, always looking for new talents. And I'm sorry, but if you use NPM and JavaScript, as you are since you're here, you cannot escape from us. We are 80% of NPM packages, and we have roughly 1 billion downloads per month, so whatever. So sorry about that. And let's give correct credit for this talk. Originally, this was written by this guy, Michele, which was my colleague at Nearform. Originally, it was from him, so any incorrect things to say in a formal way you hear from me today is his fault, not mine. Sorry. So you can complain to him on Twitter as well. Now, why do we need encryption? Why do we need to encrypt our data when we send over the network? Why we need end-to-end encryption? There are several reasons. First of all, network communication are insanely complicated. For instance, I chatted with my wife today. She's in Italy, obviously. And in order to my message to get to her in Italy, there are several levels of hopping over the network, from Utah to somewhere probably New York, somewhere in Spain where the other side of the sea channel ends, and so forth, back to Italy, right? Each of these segments can be compromised, and if people are willing to learn to my messages, I mean, I don't know why they want to waste their time. Up to them, they can do that, and that's a problem. Even if you switch to a more local environment, for instance, wireless network can be extremely insecure, especially if they are badly configured or badly designed. Anybody remember the WEP standard, right? It was easy to sniff. That's a problem. And if you bring this to an even closer environment, think about LAN cables. Strictly speaking, this could be compromised. If you believe in conspiracies, anybody with physical access to your machine might install a counterfeited LAN connector and sniff your data. I mean, I don't even know if this thing exists. Why they should not? Anyway, right? Probably. But let's start with the foundation of remote sending of a message. Let's start with just send a message in the old fancy way using messenger pigeons. Now, they were used in the medieval areas to send messages from point A to point B, but there was a problem. If you shot this little guy down, you can read the message. That's it. Now we are in more civil war nowadays, probably would try just to get them to our place with food or something like that, but yet we can read the message which is intended to be sent to someone else, which brings to the point that was not an encrypted channel at all. It didn't work, simply didn't work. Now, let's start in a more formal way. What is the description of encryption anyway? What is the formal description of this encryption? Is the act of putting information into a special code, especially in order to prevent people from looking at it without authority. This is the Oxford Dictionary. In other words, we want to mask the message in order for anybody but the authorized person to read it. That's the short gist of it. An example for that is the Caesar cipher, which is one of the oldest encryption method available. Was pretty easy, and that's for a reason that we can easily see not really secure, but it was the very first example, the Caesar cipher. How it works? Very simple. The only parameter that the Caesar cipher has is how much are you shifting the data to encrypt the sentence, and how I have to shift backwards in order to decrypt the data. In this case, I have the word London. I choose a shift of +3, which is equivalent of -23, since we have just 26 characters in the alphabet. So we get L gets to O, so M, L, M, and O. Then we have O, we get to a R, O, P, Q, R. Then we have N, which becomes a Q, P, Q, R. That's it, a P, O, P, Q, sorry. Then we have the D, which becomes a G. The O, as we already saw, becomes an R, and the N, as we saw, becomes a Q. Now, there are several problems in this algorithm, which we're going to see in a bit. But let's dig further. Trivial question for the audience. Do you know that guy on the right-hand side? And does anybody know where its name comes from? Go for it. Nice. Basically, this is HAL 9000 from the movie 21 Space Odyssey. And he gets his name from being a shift -1 of the words IBM. So I becomes an A, an H, B becomes an A, and M becomes an L. Very basic Easter egg, but whatever. And it's a Caesar cipher. So as you can see, this algorithm is used in places you would not expect it. But let's go on. A bit pain for the oldest of one. Do you recognize this thing by any chance? Anybody? Come on, raise your hand if you know it. Go for it. What is that? Yes. So that's the rotate 13 or rot 13 for short, which was used back in the days where internet was not so evoluted as we are. So people basically try to find a way to write encrypted or not spoiling messages on news groups or something like that. And the rot 13 is just a Caesar cipher with shift plus 13 or minus 13 in this case, because that's the same, in order to encrypt a message. For instance, the hello world becomes URYYB. Pretty easy. So as you can see, this method is used in places, once again, you don't really expect it. Now, it brings to the point. Can you think of a reason why Caesar cipher is not secure? Go for it. Just shoot.
You can figure it out easily.
You
get the original data.
Okay. Anything else?
If you know the key, you can decipher it.
Yes. But what if you don't know the key?
You have 26 options.
Yes. One more.
It takes 24 times to figure it out.
Yes, brute force is an option, but there is also another thing. Think about this. What can you notice in this London example?
You can see which ones are vowels, common letters.
Yes. Yes, that's called the letter analysis. So the problem is with Caesar cipher. First of all, it's very easy to brute force it since it's just 26 possible permutation. But even if you don't want to brute force the message by any chance, if you start analyzing, if you basically know the language the word is supposed to be written into, for instance, this graph is for the English language. I suppose British English for American would be slightly different, but let's bear with me on English. You can see that, for instance, the most common letter in the English language is E. So you can just look at that, says, okay, let me find a E in this word. If I find it, and then eventually I have 12% percentage of getting it, I can decipher the entire sentence. Of course, is not secure. Now, what is a good algorithm? A good algorithm is this one. It must have this characteristic. It must be public, and all the security is in the parameters. Why is that? If you have a private algorithm that might be or might not be mathematically strong, but probably is not, if the people steal the algorithm, they also steal your data, no matter how you encrypt the message. That's the problem. A public algorithm can be easily validated by people and be continuously reevaluated for security and flaws, because the security is just in the parameters. For instance, question, who is still using MD5 for anything in his daily life? Don't. It was cracked. I mean, probably you can use for not critical data, but for very sensitive data, never use MD5 because it was cracked by some researcher, and that's why it's basically considered now a deprecated algorithm. Of course, if you just have to have a local index of your files, MD5 is fine, but for sensitive data, don't use MD5 anymore. I now know that, if I'm not mistaken, even SHA-1 is not secure, considered not secure anymore. Now you have to use SHA-2256, for instance. So as you can see, as time goes, we are continuously reevaluating all the algorithms that are considered secure or not secure. And this is only because the algorithms are public. Because if black hat hackers are violating your data, they're never going to tell you, oh, your algorithm is not secure. Makes no sense, right? So make sure your algorithm is public. Second, the security must be in the parameters. Even if I know your complete algorithm, if I don't know the parameters you're using for this algorithm, I cannot decipher your data. Now remember, for each algorithm in this world, brute forcing is always an option. Now the key here is that if you see it there, I say not impossible, I say unfeasible, which means if somebody is interested in my, for instance, health data and wants to get in my health data by brute forcing, and it takes them 100 years for deciphering my health data, in 500 years I will be longly gone and I don't care if they read my health data. That's the key. Make sure that it takes so much time for them to use brute forcing that they cannot use brute forcing. That's it. That's the idea. Now, what are our options today? One of the options we have now is AES, enforced by the NIST, which is the National Institute for Standards and Technology, if I'm not mistaken, which is researching on that, and said EAS is good. You can use it. This is a secure symmetric block algorithm, which means that both parties must use the same key, which brings to the next point. We have to make the communication secure. Now, if we use AES, we're fine, but how do we share the key? Either we know in advance and we never share this key over the wire, which might possibly be. So if nobody cannot physically listen to us, they don't know the key, or we have to find a way to share this key over the wire. Now, since the key must be acknowledged before doing the encryption, this cannot be encrypted. The key sharing cannot be encrypted, which is a problem, because anybody could steal the key. Question for the audience. Do we have a solution? Raise your hand if you think no. Okay, nice. Tricky question. Of course we do. These two guys are Diffie-Hellman. And if you are in encryption a little bit, you probably have heard about them. The Diffie-Hellman algorithm is named after these two guys, which were researchers. And you will be surprised from now on how simple this algorithm is. Basically, the Diffie-Hellman algorithm brings security in the insecurity world. It has strong mathematical basis, but you will be surprised to see how this strong mathematics is insanely simple to implement. I will show you a real example of how simple it is to implement, just using three mathematical operations, actually just two, and their properties. That's it. I mean, really second grade school, not even high school. And it's fast and easy to implement. The only remark here I want to make is that once you initially compute the key, given that the Diffie-Hellman is secure, but is always brute forcing possible, it's always a good idea to rotate the key regularly, because even if brute forcing is unfeasible, there is always the Murphy law. Somebody might try to brute force your key and guess it on the first guess, so rotate continuously. Because in this case, if this happens, on the next message, you skip it and you change to another key, and this basically makes it impossible to guess your key. But that's another thing. Now, it's time to paint. I want to leave brief credit to Michele. When we initially delivered this talk the very first time, we literally paint with brushes on the stage. It was a much smaller stage now. It's impossible to do that today, so I switched the real brushes and painting to horribly endlessly written stuff on my iPad. So I forgive for the appearance of the next few slides, but the idea is still the same. It's still art. Let's go with it. How we do generate a shared key using Diffie-Hellman between two parties. Since I want to be academically correct, I will name the two parties Alice and Bob, like you can see everywhere on the net. And the idea is that Alice and Bob will share over that public channel on the central part. Now, the way to Diffie-Hellman work is that both parties have a public and private keys, and of course only the public key is shared to the other parties. Does it resembles anything about SSH keys? Same idea. And using their private key and the other party's public key, they will generate a shared key which is identical. That's how it works. Let's translate these two colors. Alice starts by generating the private key, which is the red one, and the public, which is the blue one. Bob does the same with different parameters. We'll get to the same color, which is blue. I will show you why it gets to the same parameters, which is the blue part, and the yellow one. Basically, they sum it up and they get different colors. They get purple one and they get green one. So this is the basic color addition, right? We have we use when we're our children, basically. Now, next, they share all the parameters of the communication, which holds one private part and one public part, to the other party. So Alice gets the green from Bob, Bob gets the purple from Alice. And then, finally, they add up the other private part that the other party doesn't know about, and they get to the same color. Now, bear with me that we get to the same level of brown, because it might be debatable from art addict people, but you can trust me on that. I will show you in a bit why. You get to the same brown. The brown represents the shared key. From now on, they can use this key. For instance, Caesar cipher in this case might be an idea. You can use this key to have an end-to-end encryption with shared key, and the shared key is never transmitted over the wire. That's how it works. Now, this color explanation was pretty fancy, and you probably don't believe me, so time to do some math. Let's go with math. Let's see what happens. Let's start with Alice. Alice must choose 3 parameters. And forget for my handwriting once again. The first letter is an A in lowercase, which means it's the Alice private key. G is a base that we are going to use for multiplying, to basically elevate to the power of something. And P is the modulo we're going to use to trim down the parameters. Now, usually the G and P parameter can be public because it doesn't matter. So that's the blue part I was showing you earlier, which are shared. And usually for sake of simplicity, G is usually chosen to be 2 because in IT it's very easy to do power of 2s. So G, let's assume is 2. P can be anything. And basically, Alice generates his public part by doing G elevated to the power of A modulo P. That's it. That's the key A. And it sends this public key to Bob. Done. Now we are on Bob. Bob receives already G and P, so it doesn't matter, and he chooses B, his private key, and it does KB equals to G elevated to the B modulo P. These are the 2 operations. Once computed, it sends KB to Alice. After this, both parties make the same calculation. Alice does the operation KB, which is, once again, Bob public key, elevated to A to the power of modulo P. Bob uses the Alice's public key to do KA elevated to B modulo P. Now, as you can see in the notation, I chose the letter K in both places because they get the same result. K without any letter below, it's the shared key for this communication, and we get to the same thing. Now, if you don't believe me, since this is the last talk of today, I'm gonna torture with a little mathematical demonstration. So let's start with very top. We can start from Alice or from Bob. I chose to start in this case from Bob. Bob receives Ka, elevates to the power of B, mod P. So we can replace Ka to the original definition, which is Ga to the mod of P, elevated to B again, mod P. Using the properties of powers, we can say that is equivalent to G elevated to the A per B modulo P. We can reverse, of course, for the commutative property of the multiplication to GB and then multiplied by A modulo P. And then we can extract G elevated to B modulo P to the power of A modulo P again, because it doesn't matter. And we get KB to the power of A modulo P. So as you can see, as is underlined in green, we get to the both definition of how the public key is processed after be received by any party. That's the idea. If you still don't believe me, I can torture you even more by showing how it works. Let's make a very practical example. I set to B, A to B5, B to B6, G as said I set to 2, and P I set to 10 because I'm lazy, so I'm gonna use modulo 10 in order to get just the last digit of every operation, which is the very, very cheaty part. Now, let's start. Ka is G to the power of A modulo P, so it's 2 elevated to 5 modulo 10, so 32 modulo 10 makes 2. That's it. Similarly, KB is J elevated to B modulo P, so 2 to the power of 6 modulo 10, 64 modulo 10, 4. We get our public keys. That's it, pretty simple, right? Now, let's make the final calculation. Let's calculate the shared key starting from the public key of Alice. So we get KA to the power of B modulo P, so it's 2 to the power of 4 modulo 10, 16 modulo 10 makes 6. On the other way around, KB to the, oh, there is a missing A there. There is a missing A. KB to the power of A modulo P, so 4 to the power of 6 modulo 10, 496 modulo 10, which makes 6 again. We get the same number. So remember, this thing with the much more decent parameters, because of course 2 power 10 would be very stupid to brute force, is literally what empowers end-to-end encryption on our channel, on our devices, application and systems. Because the Diffie-Hellman is very, very good, well proven, and mathematically strong. Because one thing why I used colors, and I forgot to mention earlier, is that once in both parties you get to the brown, for the property of colors, you cannot go back to the original components because you could go from, purple plus yellow and you get brown, but there are several other combinations. That's the same idea on the mathematical side. Once you get 6, in how many other operation ways you can get 6? Think about the quizzes that you find online about mathematical series. There's no way from a number to establish where it comes from. And that's the idea why Diffie-Hellman, if the parameters are correct, works. And that's why Diffie-Hellman, even though the algorithm is public, works. Which were the 2 criteria I established earlier for a robust and secure public encryption algorithm. You know how, you know part of the parameters, you cannot go back to the other parameters, even if you know the result. That's the idea. That's math. Now, one last thing on which I like to close usually my talks, some very smart quotes from Adi, way smarter than me. In this case, the decision we make about communication security today will determine the kind of society we live on tomorrow. Think about government intrusion, give about hacking, being our data be secure, and so forth. When you deal about security, encryption, processing data, and so forth, always think about who are you impacting, your users, your government, your nation, anybody else. Fun fact, if you think who that guy is with Phil Diffie, yes, he's the guy from the Diffie-Hellman algorithm. I found a very good quote from him, so why not include him there? And that's all I have for today. If you have any question for me, I'll be on side of the booth. If you're interested in joining Nearform, come talk to me. If you have your enterprises interested in doing business with Nearform, come to me as well. I'm there. You can recognize by the fancy yellow shirt. And thank you very much.
Thank you, Paolo.
Thank you.